Okay, in this video, I want to talk about integrals now. Um, so in Calculus 2, you learned about antiderivatives and geometrical interpretation of area under the curve. And I want to talk about how this extends in the world of vector functions. Okay, so I want to first cover the interpretation of the accumulation of change, right? So if your vector function represents the rate of change of something, then when you compute the definite integral, you are computing the accumulation of change for each component separately. So if you have, for example, like a velocity in x, y, and z component, then the definite integral will give you the total displacement from time A to time B at the end. So I hope this is not too much of a surprise, right? So it's kind of like doing component-wise definite integral. So might as well do an example problem. So know that the Calculus 2 stuff hasn't gone away, right? So in Calc 3, you have to be doing Calc 1 and Calc 2 component-wise. So let's say this is a particular rate of change that's given in x, y, and z directions. Let's compute the antiderivative. So computing antiderivative is going to be term by term. And let's say the x component looks something like this. And you can pull out the vector base like I away from the integral. So you're just doing the integration in the components. Okay, so for this integral, the way to do it would be a u substitution, because if you take the derivative of the bottom denominator, then we don't have 2t dt in the top, but we have t times dt on the top. So we could just kind of turn this 2 into 1/2. And then the integral becomes 1/2 1 over u du. Okay. And antiderivative of 1 over u is going to be natural log of u, but u is t squared plus 1. So that's the ith component. Okay, let's look at the second piece. This is the antiderivative of 1 over t squared plus 1. dt, and that's the jth component. This guy is straight up an antiderivative. You can look at the table, right? So whenever you have 1 over t squared plus something squared, the antiderivative is going to be arctan, right? 1 over like a arctan of t over a, something like that. Our a is 1 in this case, so this becomes arctan of t. I haven't been writing the constant term for that antiderivative, but I could do that all at the end. Okay. For the final integral, so it's easier to do it with partial fractions. So t squared minus 1 happens to be t plus 1 times t minus 1. So partial fraction is probably the easiest way to do it. Okay. So if I multiply both sides of the equation by t plus 1 times t minus 1, I get 1 is equal to a times t minus 1. The t plus 1 cancels with the t plus 1 there. and b times t plus 1, and the t minus 1 cancels out with the fraction there. And this is supposed to be true for any t whatsoever. So if I plug in t equals to 1 here, I get 1 is equal to 0 times a times plus 2b, which means b is equal to 1/2. And I could get something similar. If we plug in t equals to minus 1, then this term drops out because we'll get minus 1 plus 1, which is 0. And then here I have 1 is equal to negative 2a, which means a is equal to negative 1/2. So the antiderivative of this expression is going to be negative 1/2 over t plus 1 plus 1/2 times t minus 1. Okay. And then this is a straightforward u substitution now. So you could say u is equal to t plus 1 or u is equal to t minus 1 separately. And then we can get the antiderivative. So this is going to be negative 1/2 natural log of t plus 1 and positive 1/2 times natural log of t minus 1 plus some constant vector. I'm just going to call v. Okay, so that's the antiderivative of this particular vector function. And if I wanted to compute displacement, I'd plug in t equals to b value and then subtract what you get when you plug in t equals to a value, just like we do with a regular definite integral problem. Notice how this is just a way for me to be able to ask you Calc 2 questions, right? In fact, I'm giving you 3 different problems in a single problem here. Okay. All right, so you can't forget about Calc 2 stuff. Another interpretation or integration is, of course, the area under the curve interpretation. So in 2-dimensional, like a single variable calculus, we can interpret the definite integral as this area underneath the curve. And if the function goes below the curve, it's the negative of the area above the curve, right? So that's the interpretation we get. When we come to the parametric setting or the vector function setting, things get a lot more flexible, and you get to compute area enclosed by a curve. So maybe you can already see the really ugly region that I've drawn with the arrows here. So if you write down a formula for parametric curve that goes through some curve where it starts and stops at a particular point. So let's say, so in 2 dimensions, you had the leftmost point and rightmost point as the beginning and end of the definite integral. In the parametric setting, you're integrating with respect to t, not with respect to x. So you're plugging in the starting time and ending time of the parametric curve. So maybe it starts at any particular point, and then goes and traces a region, and then comes back to the same point at some t value beta. So we're integrating from t equals alpha to t equals to beta. Okay. Then I claim that the area enclosed by this curve is given by the component function for y value, multiply by the component of the x value differentiated, and you integrate. And here, the area needs to be enclosed clockwise direction and not the counterclockwise direction. You could do it counterclockwise, it'll just count the area as negative. So that's good to know. And you might be wondering, well, why would it be that way? Well, the formula kind of gives you a hint of what's happening. So in 2 dimensions, y is just the function itself, f of x. And we can get the area underneath the curve by kind of adding up these rectangles, right? The height of the rectangle is given by f of x, and the width of the rectangle is given by dx. Similar thing is happening here. For any particular point, we're multiplying the height of the rectangle multiplied by the change in x. But change in x is multiplied by, instead of dx, we're going to do change in x times how much time it took. So rate times time gives you the change in x. So let me kind of draw exactly what's happening here, and hopefully I can convince you that this is going to give you the area. Okay, so I'm just gonna do a portion of this picture. I'm not gonna do the entire like ugly gack area. So let's say I want to compute this area. And as I might do in Calc 2 class, I'm imagining this area as rectangles. So the height of the rectangle at any particular point is going to be y of t, so some function of time, and the y component of it. And the width of the rectangle is how much you travel in x direction. Well, how much you traveled in x direction is, well, how fast were you going to the right times how much time did you go to the right. So dx dt, or that's the same thing as x prime times dt will give you that. And I'm thinking of dt as a small amount of time. Okay, so as you travel through here, you are multiplying this area of these infinitesimal rectangles by given height, and how far you travel to the right gives you the thickness of the rectangle. Now we're going to change some direction, so it's going to look a little bit funky. Let me change the color of the pen as well. So as the curve kind of doubles back to the left, in this picture, the height of the rectangle is still positive, right? So now I'm going to draw this rectangle as blue. Okay, as the curve is traveling to the left, y is positive because it's above the x-axis. X prime is now negative because it's traveling to the left, right? So times dt, the change in time is going to be positive as time counts upward. So this area right here is going to be subtracted from the total area as it computes to the left. Okay. All right. And then once it tries to double back to the right again, it starts counting the area underneath the curve as positive now. So I'm going to draw it by green area. and it continues to, as you go to the right. Okay, so let's try to see what area did this compute in the end, right? So we had a positive area going this way. We had negative area going this way, and positive area going this way. Certain areas were counted more than once, right? So let's see how it was counted. So over here to the left, this was counted positively once. So that's good. This area right here that I'm looking at, that was counted 3 times, right? Once going to the right, once going to the left, and once going to the right. So it was counted positively twice, and then counted once negatively. So the net area that was computed was just positive once, because being counted positive once and negatively once cancels out, right? In this region, right above it, when he was going to the right the first time, it went underneath, so this area was not counted. But when it went back to the left, it was counted negatively once. And then when it went to the right, it was counted positively again. So negative and positive area that was counted canceled out, and it's as if we didn't count that area at all. And then finally, after it started going to the right, this big region was counted positively once. Right? So what does this area turn out to be? Right? This is the area we wanted to count, right? This portion was counted once. This portion was counted once in net, right? Twice positively and once negatively. This region right here was never counted because positive and negative canceled each other out. And everything else was counted once. So you could have a curve that kind of doubles back, and it counts the right portion once. And even if it doubles back, it cancels out in a nice way such that area is counted. Now, that explains how the area is counted for these portions. And you might be wondering about where it dips below the x-axis. That's counted correctly as well, because when it dips below, the y is negative. And if it's moving to the left, x prime is negative and y itself is negative. So this is being counted as a positive area over here. Okay, so it works out. And this is amazing, right? Like in Calc 2, you may have computed like area between curves, right? So if you were clever, if you had an area that looked like that, you were able to compute it by taking 2 integrals and subtracting it. But actually, in a parametric setting, you can get like a really ugly looking areas computed correctly with a single integral. Okay, so I don't really have a really ugly example prepared to present here, but I could give you one example, which is an example of an ellipse, right? So equation of an ellipse is given by this formula right here. Let me use a different color pen. And then we could solve for y. Okay, and then multiply by 9. And we could square root and take the positive square root. That would be above the x-axis there. And then if we integrate this from the left endpoint to the right endpoint, you can get the area above the x-axis, and then you can multiply by 2. This is how you might have computed this integral. This integrand, you might have to use trig substitution. So that's how you might tackle this problem in Calc 2. Let's do it in the Calc 3 way using parametric equation. Okay, so what do we have to do? So we first need a curve that traces the ellipse. Cosine and sine will wraps a unit circle counterclockwise. We have to change that a little bit. If we stretch in the x direction by 2 and stretch 3 in the y direction, you can get the ellipse in the size that we want. This wraps around the area in a counterclockwise direction, which is gives you the opposite of the area we want, but that's okay. We could just put a negative sign in front to get the positive area, right? If you don't remember if clockwise or counterclockwise is the correct direction, we could always take the absolute value, right? But I assure you, it should be clockwise. So this will give us negative area. So how do I set up the integral? Okay, so it's y times the derivative of x, and we're going from a particular value to another particular value. So it'll wrap around the whole thing in 2 pi. So that's going to be my alpha and beta. The y value is 3 sine t. And x prime, I have to take the derivative of this guy. So derivative of cosine is negative sine. Okay. And I know that this is going to be negative the area we want. So I'm going to put negative sign in front just to anticipate it, to cancel it out so I can get the positive area at the end. Okay, so let's pull out all the constants. So I have a 3 here, negative 2 here. Pulling that out and combining with this negative, I'll get positive 6 on the outside. And I have 2 factors of sine, so sine squared here. The way to calculate this is to use trig identity. Sine squared is equal to 1 minus cosine 2t over 2. So the over 2 part, 1/2, I'm going to pull that outside of the integral. So that's 6 and a 1/2 will make a 3 on the outside. Okay. And then I have 1 minus cosine 2t dt. All right, let's find the antiderivative now. So antiderivative 1 is just t. And antiderivative of cosine of 2t, well, I have to do a u sub, right? So u is equal to 2t, and that will contribute 1/2. So this is what I get for antiderivative. And if that went too fast, I could double check it for you. The derivative of sine is cosine of 2t. But then by chain rule, I have to multiply by derivative of 2t, which is 2, which will cancel out with the 1/2. So that is the right antiderivative. And then t is going from 0 to 2 pi. So we'll plug those in. Okay, so this is what I get when I plug in 2 pi. And then if I plug in 0, here's what I get. And sine of 4 pi and sine of 0, they're both 0. So the only contributing term is just this 2 pi here. So we get the area is 6 pi. And that's it for this problem. Okay, so I think it wasn't a really complicated looking area, but I think that was even already simpler than how you might have done in the Calc 2 class. So I'll count that as a plus. Okay, I think I want to end the video here. I will see you next time.